In the last video, we saw springs in series. In this video, we will look at springs in parallel. So, the question is, find the time period for the arrangement for the following arrangement. We have a spring, a mass, a block of mass m, and then spring, and then attached to the wall. So spring constants k1 and k2 and the mass of the block m. So let us try and solve this question. So if we consider the equilibrium position to be here, and then we displace the block by a displacement of x from the equilibrium position, then notice that this displacement from the equilibrium position is also the extension or the compression in the springs with k1 and k2 spring constants. So if I redraw, then k1 gets extended by x and k2 gets compressed by x, because this was the equilibrium position. Earlier the mass was here. Now the mass has moved by, the block has moved by x distance over here. So this distance is the extension, which is x. Similarly, the compression is in this spring, in the second spring, is also x, because earlier the k2 spring was all the way up to here, and then it has now compressed by x to be in this configuration. So the compression or the extension or the change in the lengths of both the springs will be x. So let us write down the restoring force. So restoring force for the first spring would be minus k1 times x, and in the second spring it will be minus k2 times x. So the first spring is getting extended by x, second spring is getting compressed by x. So the change in lengths is going to be the same in both the springs. This comes from Hooke's law, that the restoring force is negative of the spring constant times the displacement. So now we have the total restoring force. So see that both these restoring forces will act on this block of mass m in the same direction. Why so? It's because this k1 spring got extended, so the restoring force on the mass is going to be in this direction for k1. So this is F1. Now the K2 spring got compressed. So even for this K2 spring, the restoring force is going to be in the same direction. So the net restoring force on the block total restoring force on the block is going to be F is equal to F1 plus F2, which is nothing but minus K1x minus K2x Now from Hooke's law, we know that F is restoring force is minus kx. So from this expression out here, we come to know that the effective spring constant is k1 plus k2. This is effective spring constant. So effective spring constant is k1 plus k2, and hence the time period t is 2 pi square root m over k being the effective spring constant. This is nothing but 2 pi square root m over k1 plus k2. So this is the solution. This is the time period for this arrangement. Now let us look at a slightly different kind of an arrangement. Slightly different kind of an arrangement. So if we look at the following arrangement, let's look at this arrangement right here. So this is k1, this is spring constant k2, and this is block of mass m. Let us just try and see this configuration as well. So this is the equilibrium position, and we displace the block by x. So both these springs with constants k1 and k2 would have the same extension x. So the restoring force would be in this direction from both the springs. So if we write down the restoring force, this is from spring 1, this is from spring 2. So if we write down the restoring force, we see that F1 is equal to minus K1 x, F2 is equal to minus K2 x. So total restoring force will be the sum of this. Both are acting in the same direction. Total restoring force on the block which from Hooke's law is minus kx k being the effective spring constant. So k is equal to k1 plus k2, the effective spring constant, and so the time period t over here is again the same as what we obtained in the previous configuration. So same effective spring constant and same time period. So this configuration right here, this configuration is similar or same as this configuration over here, and this configuration is what is known as springs in parallel. So this is springs in parallel. So if we have, let us generalize this from 2 springs in parallel to n springs in parallel. So if we have n springs in parallel, let us say if we have n springs in parallel, and then a block of mass m is k1, k2, these are the spring constants, k3, so on up to kn. So in this configuration, our effective spring constant would be the sum of each of the individual spring constants. So this is for springs in parallel, and note that this expression looks similar to or analogous to resistors connected in series. So we saw that in the previous video that if springs are connected in series, then that is mathematically equivalent to resistors in parallel. And in this video we saw that springs connected in parallel is mathematically equivalent to the situation of resistors connected in series. So this solves this question. We saw springs in parallel in this video.